Hello everyone. Now I am going to discuss the speed control of induction motor by injecting EMF in the rotor circuit. Induction motor is almost a constant speed machine. However, in many applications, the speed control is required. There are two types of induction motors. One is a squirrel cage induction motor. Another one is a slip ring induction motor. For squirrel cage induction motor, there are three types of speed controls. One is stator voltage control, second one is pole changing control, and third one is frequency control. Using these three techniques, the speed can be controlled below synchronous speed. And these three techniques are well discussed in many textbooks. Coming to slip ring induction motor, there are two types: rotor resistance control and injecting EMF in the rotor circuit. Using rotor resistance control, the speed can be controlled below synchronous speed. This is also well discussed in many textbooks. By injecting EMF in the rotor circuit, the speed can be controlled below as well as above synchronous speed. This topic is discussed in very few textbooks, so I want to present a lecture on this topic. Before discussing the concept, I would like to discuss some basic concepts. This is a phasor diagram of induction motor, and on the rotor side, the rotor slip can be given as S equals to Ns minus N by Ns. Ns is the synchronous speed of rotating magnetic field. N is rotor speed. I2 is rotor current. I2R2 is rotor resistance drop and is in phase with current. And I2SX2 is rotor leakage reactance drop and it is in quadrature with current. And E2 is rotor induced EMF at a standstill, and it is constant. The magnitude of E2 depends on stator to rotor turns ratio, and SE2, the induced EMF in the rotor under running conditions at a slip of S. Under running conditions, the voltage equation in the rotor circuit can be given as SE2 equals to I2R2 plus JI2SX2. As the rotor windings are short circuited, the rotor terminal voltage is 0. The magnitude of rotor induced EMF SE2 depends on the relative speed between synchronously rotating magnetic field and rotor. At standstill, the rotor is stationary, the slip is 0, the rotor induced EMF is maximum. If induction motor is singly excited, that means if supply is given only to the stator, the machine would not run at synchronous speed. In case if it runs at synchronous speed, the slip S is 0, the rotor induced EMF is 0. At no load, the rotor runs nearer to synchronous speed, the slip is nearer to 0, the induced EMF in the rotor circuit is less. As machine is loaded, the developed torque dominates load torque. The speed falls till developed torque equals to load torque. When the speed falls, the slip increases, the rotor induced EMF SE2 increases, rotor current increases, and power drawn from stator increases. Onto the stator side, I1 is stator current. I1 is stator current. It is a sum of two components. I0 is no load current and I2 dash is rotor load component. I1 R1 is stator resistance drop and I1 X1 is stator leakage reactance drop. E1 is induced EMF and E1 dash is the supply component opposing induced EMF. and V1 is supply voltage. For discussing the concept of speed control of induction motor by injecting EMF in the rotor circuit, let us assume that induction motor is ideal. Okay. For that, the stator leakage impedance is neglected, R1 JX1, and rotor leakage reactance is also neglected. Okay. The stator voltage is taken as a reference along positive y-axis. The stator draws negligible magnetizing current which lags supply voltage by 90 degrees. The stator flux, the mutual flux, is in phase with rotor, the magnetizing current. The rotor induced EMF SE2 lags flux by 90 degrees. Let us also assume that the rotor drives a constant load. When the rotor drives constant load, the rotor current is constant, and the power input to the stator is also constant. Yeah. Let us discuss the voltage injection in phase opposition. And SE2 is the voltage induced in the rotor circuit with slip rings are short circuited. For speed control of machine, a three-phase external AC voltage source at slip frequency is connected to the rotor circuit through slip rings. When a voltage of EI is injected in phase opposition, okay, the net voltage in the rotor circuit can be given as SE2 minus EI. The rotor induced EMF SE2 is along negative y-axis. The injected voltage EI is along positive y-axis. So the net voltage equals to SE2 minus EI. So as injected voltage in phase opposition to SE2, the net voltage falls. However, as load torque is constant, the rotor current must be constant. So the net voltage in the rotor circuit should be SE2. So the induced EMF in the rotor circuit should increase. Hence, the speed of the rotor falls so that S1 E2 minus EI equal to SE2. S1 is new slip corresponding to reduced speed. If magnitude of EI is further increased, the speed falls further so that the resultant voltage in the rotor circuit is SE2. Hence, if voltage is injected in phase opposition to the rotor EMF, the speed of the rotor can be controlled below synchronous speed. When the voltage is injected in phase opposition, the power is extracted from rotor circuit, and this power can be sent back to the source. So this is efficient speed control method. In case of rotor resistance control, the speed is controlled by adding external resistance in the rotor circuit. The relation between torque, speed, and mechanical power output can be given as TD times omega equals to Pm. The mechanical power output Pm equals to the rotor input minus the rotor copper loss. R2 is rotor resistance, Rext is external resistance. If load torque TL is constant, the developed torque remains constant, and rotor current I2 is constant, and the stator power input P1 is constant, and thereby rotor input P2 is also constant. When external resistance is added in the rotor circuit, the rotor copper loss increases, thereby the mechanical power output decreases. As the load torque is kept constant, as PM is reduced, the speed of the machine decreases. The speed is decreased by wasting power in the external resistance. So this is inefficient speed control. Let us consider the next case, in-phase voltage injection. In this case, the injected voltage is in phase with the rotor induced EMF along negative y-axis, and the magnitude of injected voltage is less than rotor induced EMF. As both are in the same phase, the net voltage in the rotor circuit can be given as SE2 plus EI. So the net voltage increases. Again, as the load torque is constant, the rotor current must be constant. The net voltage should be equal to SE2. So here the rotor induced EMF should decrease. So the speed of the rotor rises from its operating speed, so that S1E2 plus EI equals to SE2, and S1 is the new slip corresponding to increased speed. When injected voltage is in phase with the rotor induced EMF, the power is injected into the rotor circuit. Therefore, the power drawn from stator decreases. Here in this slide, the magnitude of injected voltage is equal to rotor induced EMF. The net voltage in the rotor equals to rotor induced EMF plus injected voltage. So as the injected voltage itself equal to SE2, the new rotor induced EMF must be 0. Okay. The rotor induced EMF becomes 0 when the rotor runs at synchronous speed and slip is 0. Slip S2 is 0. The total power required to drive the load comes from external source instead of stator. Here in this case, the magnitude of injected voltage is more than rotor induced EMF. So the net voltage equals to SE2 plus EI, as the magnitude of injected voltage is more than rotor induced EMF. The new rotor induced EMF must be negative, so that S3E2 plus EI equals to SE2. So the rotor runs above synchronous speed and slip is negative. In this case, the more power is injected into the rotor circuit than required by the load by external source, and the motor runs at above synchronous speed. In conclusion, if injected voltage is in phase opposition, the speed can be controlled below synchronous speed. And secondly, if injected voltage is in phase with rotor induced EMF, there are 3 cases. In the first case, if EI is less than SE2, the speed can be controlled below synchronous speed. If injected voltage equals to rotor induced EMF, the rotor runs at synchronous speed. If magnitude of injected voltage is more than rotor induced EMF, the speed can be controlled above synchronous speed. This type of control is used in following applications. The first one is a Scratch motor. It is a conventional machine in which the speed can be controlled below as well as above synchronous speed. The second one is a static Kramer drive. This is in this machine the speed is controlled below synchronous speed. The third one is the static head-based drive. In this machine the speed is controlled below and above synchronous speed. Coming to fourth one, in wind power generation, if a squirrel gauge induction machine is used, the machine should be driven above synchronous speed to operate a machine in generating mode. If slip ring induction machine is used, if slip ring induction machine is used, it is fed from stator as well as the rotor. The corresponding machine is called as doubly fed induction generator. And in this doubly fed induction generator, if voltage is injected in the rotor circuit, the machine can be operated in the generating mode below as well as above synchronous speeds. Thank you for watching the video and wish you good learning.